So you may have already watched a video on graphical limits introduction. And what I'm going to try to do is finish out the entire limits chapter slash review in this one video. I'm going to try to make it short, but you've already seen the time. It probably didn't turn out to be short. But I'm going to try to hit basically everything in the laundry basket of limits in a few examples. So let's start off with this one. Your job would be to say, hey, I would like to take this 3 and plug it in to get my answer, but as you would guess, when I plug the 3 in, it might work out on top, but in the denominator I get a 9 minus a 9, which is a 0. Denominator of 0 explodes the fraction, can't do it. So the way the terminology I've used is we're going to use some version of algebra trickery. And algebra trickery is going to let you change what this looks like, and something good's going to happen, maybe, when you do that. In this case, those two would reduce, and you get this new expression, and when you plug the 3 in, now it works. So keep this in mind, kind of an overriding principle. When the plug-in doesn't work, one of your options is algebra trickery. There's a lot of algebra out there. I happen to use a GCF and difference of two squares factoring, but there is a lot of algebra out there. So now branching off of that, I want to talk about this equation, which is the star of the show. And there's 3 things I know about this equation by this one little exercise. First of all, I know there's a vertical asymptote at x equals -3 because my final result after factoring and reducing had a -3 that is going to blow up that denominator. But there's a point discontinuity at x equals 3 because x equals 3 was something that would have blown up the denominator, but its trouble spot got reduced away, making x equals 3 a point discontinuity. That's one of these things. So difference between those two. And finally, this is a little bit of mental math, so I'm going to go over how we get this. But I know that this graph has a horizontal asymptote of y equals 4. Now, how do I know that? Horizontal asymptotes are found by evaluating the limit as x approaches either infinity or negative infinity. You need to do them both, but I'm just going to do positive infinity here. And hopefully you recall that as I approach infinity, I would kind of daydream about doing a t-chart that looks like this. Now, if I was approaching negative infinity, I would just have negatives in front of all those. And I'm asking myself, what's the trend in my y values? Well, when you do something like this, what you need to remember is you only want to focus on the 2 most powerful terms. Here's the most powerful term in the numerator. Here's the most powerful term in the denominator. So you don't care about those other ones. Now, as I approach infinity and I just compare these two, they're always going to be separated or in a ratio of 4. So I know that limit value is 4. Thus, that's also how I find horizontal asymptotes. If I were to approach negative infinity, because this is squared and this is squared, I would end up with a positive divided by a positive, and I would still end up with a positive 4 in this case. So these are 3 things I know about that equation. I'm going to branch off a little bit more and do a little bit more work with that equation. And what I'm going to do is I'm going to investigate a little bit of our asymptote. We said we had an asymptote at x equals -3. So if I want to investigate that, for example, I wonder, is my graph going up there for this asymptote, or is it going down here? And I could investigate the other side as well. Well, to investigate the behavior of the graph to the right side of x equals -3, I look at the limit as x approaches -3 from the right-hand side. All right, so now You see here my answer is negative infinity, which is telling you my graph is doing this. As a reminder of how I got that negative infinity, I take this thinking and I employ it into what I call an intelligent t-chart. Intelligent t-chart meaning I'm going to select numbers that approach negative 3 from the right. And what I'm going to do, instead of computing all the y values, I'm just going to think of the trend. As my x gets closer to negative 3, my numerator is 4 times close to negative 3, so it's closing in on negative 12. My denominator, as I plug in numbers closer and closer to negative 3, makes this thing become very, very tiny, but always positive. So I have a trend of closing in on negative 12 in the numerator, and then the denominator is getting tinier and tinier. A way to state this in a different way, it's kind of like this is happening. Those are negative 12s, aren't they? If this were the trend that's happening here, these values are closing in on negative infinity or trending towards negative infinity. So, by the way, going back from the other side, things that I know, vertical asymptote at x equals negative 3. We just worked on that. Horizontal asymptote of y equals 4. Point discontinuity at x equals 3, so I'm going to have one of those. And the limit as x approaches 3 of this thing is 2, which means as I approach x equals 2 from the left, point discontinuity, and as I approach it from the right, I'm closing in on a value of 2. So my graph probably doesn't look exactly like that. To get more insight, I'd have to do a particular t-chart, but I have the major characteristics going on right there. All right, thanks for hanging in there. We've got more to go. I have a couple of what-ifs. What if this were my problem I was working with and I was thinking about now the horizontal asymptote? And remember the horizontal asymptote, what you're doing is you're thinking about the limit as x approaches positive infinity, or you're thinking about the limit as x approaches negative infinity. That's how you find those asymptotes. So just to keep our thinking pretty simple, I'm going to think about positive infinity, but you should be able to adjust your thinking. As x approaches positive infinity, if I had this equation, what I would tell myself is, you know what, I don't care about these terms. They're too small. This is the big dog on the top. This is the big dog on the bottom. Let's let them battle. As x approaches infinity, my numerator, because of x cubed, becomes far more powerful than my denominator, so I get a positive infinity answer, which means as my x values go out to infinity, my y values are going out to infinity. By the way, if I were approaching negative infinity, I would get a negative on the top and a positive on the bottom because of the cubic, so I would get something like that. Okay, now let's do another what if. What if this was the equation I was working with, and I thought about my limit as x approaches positive infinity? As x approaches positive infinity, this thing, e to the x, becomes much more powerful than the most powerful term up here. For example, if I plug in a 100, e to the 100 power is way more powerful than 100 squared times 4. If you don't believe me, get out that calculator. So the limit as x approaches infinity of this thing would be 0. I'll just call it function y. So I know that this thing would have a horizontal asymptote of y equals 0 out on the right-hand side. But if I investigate going out to negative infinity, as x approaches negative infinity, e to the negative 1,000, that's a tiny number. So my denominator, super tiny plus 2, remains tiny, but I plug in the negative infinities into here, and this becomes huge. So I get this trend of my numerator becoming huge, positive because I'm squaring it, but huge, over very tiny. So what I'm going to get is an infinity on the left-hand side. Okay, so I've rambled a little bit about horizontal asymptotes. I just have a couple more things to ramble about. Let's take a look at something like this. Maybe I can zoom in a little bit on that one. Okay, I just bring this one up because it's good to remember that you need to know the shapes of functions. In this case, natural log of x is a part of this. This is not the graph of that entire function, but it's the graph of natural log of x. So now, if I think about this, as x approaches 1 from the left-hand side, what's the trend on this thing? Well, of course, you'd try to plug a 1 in. You get a 4 in the numerator. Natural log of 1 is a 0 in the denominator. Your plug-in didn't work. So now what could you do? You could do like an intelligent t-chart. I'm going to approach 1 from the left. So that's what's happening. As I'm doing that, as my x values are getting closer and closer to 1, the trend in my graph's y values are 4 times close to 1 is 4-ish. Natural log, as I get closer and closer to 1, its values are negative, but they're getting really tiny, closer and closer to 0. So I'm heading to 4 divided by tinier and tinier numbers would be infinity, and I've got that negative sign. So my answer to that limit is negative infinity. It's just, this example is showing you once again how to think about a trend maybe in the t-chart setting. All right, here's my last rambling. I just want to remind you of this thing we call the memory limit. And the memory limit says, hey, limit as x approaches 0 of sine x over x is 1. There's ways you could calculate that on your own using L'Hopital's rule, which we haven't talked about, looking at a graph and so on. But because for some reason calculus people love to include this in so many problems, you should just memorize it. So with that in your memory banks, let's take a look at this problem. I purposely use this notation, sine squared x, which is really the equivalent of sine of x squared. They're interchangeable ways to write that. I'm going to take this problem and break it apart. Of course, I tried to plug in an x equals 0, but that blew up the denominator. And then just to remind you of other things you can do, there's more than one path you could take here, but this is the path I took. I took this thing and rewrote it as two limits. The sine of x over 2 times the sine of x over x. By doing that, this was the memory limit of 1. This, by plugging in, ends up being a 0. So doing those two individual limits, 0 times 1 gives me 0. That means the limit of this is 0. All right, I know that was a lot of information in about 15 minutes, but really, other than L'Hopital's rule, we've covered virtually everything in the limit chapter. See ya.